Welcome back. In the last video, we implemented an entire Enigma encryption path which transformed a letter A into an X, which corresponded to this path through the machine. So green here is the forward pass, yellow the reflection, red the backward pass. And we have now done that in code. Now the next challenge is for us to be able to rotate the individual rotors, because obviously on our way to build the actual Enigma machine, we have to have the ability to step our rotors, to have them rotate, right? So yeah, let's go into our rotor class and let's add a new function, which I'm going to call rotate. This will be pretty simple actually, because all we need to do is we got to say self.left is equal to, now when the rotor steps, the first letter is now moved all the way to the end. So it's now really self.left. We start at 1, and then at the very end we add in what we had at 0, right? That's all we got to do here. And then we have to do the same thing with the right-hand side alphabet as well. So self.right is equal to right and right. Now, unfortunately, I had deleted that little function that we had here, which enabled us to show the rotor. Let's recreate that. So set print self.left, print self.right, and then print nothing. And let's go to the main. Let's keep all of that for the moment. Let's go down here and say one.show, and then we'll say one.rotate, and then one.show once more. And let's run this and bring up the console. So we start with ABC on the left-hand side rotor, and the right-hand side rotor reads EKM, and now it's BCD, which is everything up here, and the A is moved all the way over here, and here EKM is now KMF, and the E is over here. So we have just rotated that rotor, and that's really all we have to do here. Now at the beginning of a new message, the operator of the Enigma machine, let's go back up here, would have set the rotors to a particular position. So you would have rotated the rotors in a way that these top left letters here, which I highlighted in blue, in this blue greenish color, would have spelled out a given key. So you could have, for example, set this to ABC. Now it's AAA, but you could have changed it to ABC as a potential message key. Now, how do we do that in code? Well, we could just say middle.rotate once and then call the rotate function twice on the right-hand side rotor. But it would be kind of nice if we could just do that in one go, have it like rotate to a given letter, and this is what we'll do next. So in our rotor class, we'll now have a new function which we'll call rotate to letter. So we don't want to be calling the rotate function multiple times. We'll do that, but within this other function, okay? So we'll say self and then a specific letter, and then we'll say self dot, well, how do we first have to define n, that's the number of rotations that we have to do. So we can do that using our alphabet, and then find that letter. That's how many steps we have to go by. So if it's an A, we don't have to rotate it. If it's a B, we have to rotate once, and this is exactly what n will be equal to if we use .find letter here. And then we'll just have to say, well, you know what, up here, I'm gonna introduce this n up here already, but initialize it to 0. And then we'll say for I in range n, do this. And now down here we'll say rotate, self.rotate, n many times. And that's really all we have to do here. So let's go back here and see if we can rotate rotor 1 to a given letter. Let's make this a G. Let's run this, bring this back up here. And as you can see, the alphabet first starts with A, obviously, but then it's G, G, H, I, J, K, and so on. And the other alphabet has rotated correspondingly. So all of these letters, well, starting with the F, and then this has rotated all the way over here, and the alphabet now starts here with G, D, Q, and so on. Oh, D, Q, and so on. The G is now at the very end. Okay, great. We can rotate to a specific letter, and with that we can set a message key. So let's code ourselves our Enigma class. So new script, which I'm going to call enigma.py. The Enigma class, when we initialize that, we'll need, well, a bunch of things. There has to be a given reflector. Simply going to call that re, and then we'll have to have rotor number 1, 2, and 3, and then we have to have a plug board, and lastly, well, the keyboard is, well, we're gonna enter it here anyway. All the components will be in there, and then we'll say self.reflector is equal to what we just threw into the function. R1 is R1, R2 is R2, self.R3 is R3. Self.plugboard is equal to that plugboard, and self.keyboard is equal to that keyboard. Alrighty, and now let's go into the main and see whether we can work with that. So from Enigma, import Enigma. Let's run that. There's an error because what's the problem here? Invalid syntax. It's a stupid error. I'm not. Did I save it? Yeah, I forgot to save it. That was the problem. Okay, so let's see if we can now make this an Enigma machine. I'm just going to call it Enigma is equal to an instance of the Enigma class. So we'll now throw in A, 1, 2, 3, the plugboard and the keyboard. Let's run this. No error. This is working just fine. And now we can take all of this and make this our encryption function. So let's say def and cipher a given letter, and don't forget about the self. We are within a class. And now we'll indent all of this twice, and the letter specified up here, and then we will return the output letter. Alrighty, so let's go here and see whether print enigma.encipher A yields our X, and it says KB is not defined, which is odd. Yeah, right. It's defined here, but in our encipher method in the Enigma class, I did not make use of self. So here, I'm not going to say self.keyboard, and this is self.plugboard. And now here, self.r3, self.r2, and self.r1. This is it's kind of annoying, but you have to go through that. Self.r1, self.r2, self.r3, self.plugboard, and lastly self.keyboard. Let's try this once more. And there we go. It's a T. That was not supposed to happen. Now what's the problem? Keyboard, plugboard, R3, 2, 1, reflector, R1, 2, 3. Do I have everything in the right? Yep, I specified rotor 2 twice. Let's run this again, and there we go. Here's our X. Okay, so let's add some comments here. I don't think we need this anymore. And here, these are the historical Enigma components. And here we are now specifying a particular plugboard. You know what? Let's move this down here. I'm just going to say keyboard and plugboard. And well, here, instead of components, I'm going to say rotors and reflectors. And down here, define Enigma machine, and then encipher a letter. Alrighty. Okay, now in our Enigma class, when we encipher something, the first thing that happens is we are rotating our rotors. Remember, this comes before. So here we'll now say pass signal through the machine. But up here, the first thing we got to do is rotate the rotors. And in the easiest of cases, this is just self.r3.rotate, right? So nothing's really happening there. Now let's see how the stepping actually works. I'm going to go up here, and here is our Enigma machine without the encryption path right before we do any rotation. So all the rotors are in their base position, that is, they have A at the top. So let's rotate that right-hand side rotor. I'm going to advance it by 1 position. Now we have the B at top and the A is now down there. And let's see what happens when we now press A. So now it's no longer outputting an X, but an N. So let's see whether we can recreate that in our code. So let's go into the Enigma class here, self_r3.rotate. We are rotating the rotors, right now only one rotor, and let's see whether that actually works. So we are now running our script again with an A. Let's run this, and it is still an X. Now what might be the problem? Let's say self.r3, did I save it? Did I save it? Let's go here, run this. Okay, still the problem, self.r3.show. And there we go. So A, B, C, D, E, F, G. This does not look like it actually rotated. Now, why may that be the case? Let's just quickly check this. Go here and say dot show, and then 3.rotate and 3.show again. So here, what's the problem? I think it just worked like right before we did this. What's the problem? I set it to 0. Yeah, obviously this has to be 1, right? Okay, yeah, that's just stupid. Run this, and now you can see here's the N. Okay, so this is working. Yeah, this is now an N. So we have successfully implemented the Enigma rotations, except that's only the right-hand side rotor, and now we have to go through this entire odometer thing where if we are at our turnover position, that is, we have our notch in the top position, then we trigger the next rotor down the line, and then this rotor rotates, and if that rotor also has its notch in the top position, it triggers the leftmost rotor, and so on. Okay, we are in the Enigma class, and let's first cover the case where all 3 rotors rotate. So we have R1, 2, and 3. When is that the case? Well, this is the case if rotor 2 and rotor 3 have their turnover notches in the top position. So if R2 dot left and 0, yeah, that's the top position in the left-hand side alphabet, is equal to R2 dot notch and, this is not important, R3 left 0 is equal to R3 dot notch. In that case, all 3 rotors will rotate. But of course, I have to add self in front of all of these, right? So self.r2, self.r3. This is getting kind of long, unfortunately. Now, if that is not the case, then we have self.r3 dot left 0. So now it's only the right-hand side. And self dot is equal to self.r3 dot notch. In that case, we're rotating these 2. And if neither of these 2 things is the case, then we're only rotating the 3rd one. Now this is how you would implement the rotor stepping, but the historical Enigma machine had this thing called a double step anomaly. And this thing was just like a quirk of the machine. I don't know if the designers of the machine intended it to function like that, but it did, and it worked, and nobody cared, I guess. And this is that when only the middle rotor also had its position, its turnover notch in the top position, then all 3 rotors would also step. So not only when both of these conditions were met, but only this one as well, okay? And this was the double step anomaly of the Enigma machine. Alrighty, now let's go over here, and yeah. You know what, the next thing that we need, before we can start deciphering some cool messages and, you know, start checking our machine, whether it works, we have to have the ability to set the key. right now, every rotor is in its base position. And we implemented this thing here where we can now rotate to a specific letter, and I kind of got carried away with the entire rotation of the machine. I'm just realizing this now. So let's go into our Enigma machine, and we'll add this as a new function here. So we'll call this set key. So we'll say self, and then we have a key, which is a 3-letter string, 1 letter per rotor. And now we'll say self.r1.rotate to letter, and we'll pick the first of the 3 letters in the key. And then we'll do this, and same thing down here with the other 2 letters in our message key. And let's see if we can make use of that. So let's forget about, well, we got to define the machine. Forget about the enciphering part. And here we'll now say set message key. So we'll say enigma.setKey, and let's just pick the key dog, okay? Dog. And let's see if that works. So print, enigma.r1.show. So here we now want to see this starting with a D, and it does. Nice. Let's go with R2. There we go. It's an O. And R3, it's now a G. But had we not set that key, they'd all start out with an A. So here's an A, and run this, and we got an A. Okay, so we can now set the key, and I think now we're really only missing the ring setting, which is the last piece of the puzzle, I believe, and for us to have implemented the real deal. But before we do that, I want to run some additional checks on whether we implemented everything correctly. I'm now going to compare this against an Enigma machine created by Michael Koss. And you can find this on his webpage, mckoss.com, and there is the Enigma simulator. And here you can specify an Enigma machine. He uses the B reflector, I believe. So let's quickly adjust this. Go with the B reflector. We have the rotors 1, 2, 3. We'll now go with this plugboard setting. So we'll also say ARGK and OX up here. Don't bother with the rings just yet. And we have our key, which we set to dog. And now we have our test message. It reads test. And let's see if we can reach the same result. So here we'll now say encipher message. So the message is equal to test. And now for every letter in the message, we'll say, okay, you know what? We'll have our ciphertext, which is equal to an empty string. And now we'll say ciphertext is equal to ciphertext plus whatever comes out of the Enigma machine. And then eventually we'll print our ciphertext. So let's run this. Unmatched parentheses. Okay, this is going to be a letter. There's another problem here. Yeah, only one. Let's run this GBFW, and this is exactly what we get out of the Enigma simulator. Awesome, so let's go with another rotor start. Let's go with cat. Let's switch this to rotor 4, 2, and 1. 4, 2, 1. So 4, 2, and 1. Change the plug board to A, B, and C, D, E, F. Save this, A, B, C, D, E, F. This is easy to remember, right? So A, B, C, D, E, F. And don't bother with the rings just yet. Let's just see whether we can produce test, which translates to QLXY. Make this cat. Let's run this QLXY. Nice. Okay, let's go for a longer message, texting, and we'll repeat that a bunch of times. Okay, just like that. But it's got to be uppercase letter for us. Now let's run this, and there we go. XROAHM. XROAHM. And I think, yeah, this is all we need so far. We have implemented the rotor stepping, hopefully correctly. At least we get the same results as we get online. You might have to try this for longer messages to see whether the double stepping works and everything associated with that. But for now, I think we're good to go. So let's move on to the next and last piece of the puzzle, which is the ring setting. Now, what is the ring setting? The ring setting, see how when we define these rotors, we just set their turnover notch. Now, in the real world equivalent, the notch was engraved onto the rotor wheel, and you could not change that engraving. But of course, people realized that it would be kind of nice if rotors didn't always step at that particular position. So what they did is they placed these alphabets on a sliding ring, and you could slide this ring and then thereby change the relationship between the wiring and the notch. And here we'll now do the same thing. So before you would encipher a message, and before you would even set the message key, you would set the rings. And let's create a function to do that. We'll call it setRings. And you would specify, well, here we are going to specify a tuple of 3 positions. And in the base setting, this is just 3 times 1. Before computers were invented, people started counting at 1 and not at 0. So yeah, 1, 1, 1 means you're not changing anything. So let's go into our Enigma machine, and here we'll have our new function. Def set ring, and here we'll now have our ring. It's actually multiple rings, so you could also call this rings, but whatever. I'm just going to call it set ring and set key, and then we'll say set ring. I know what. Let's make this rings. And then set ring is the method within the rotor class. So set rings, and then we have set ring, and here rings, come on, rings 0, rings 1, and rings 2. Okay, rotor class, gotta add that new method, def set ring, self, and then, well, some position n. And now, how does that work? Well, there's 2 things that happen. First, we are, how am I going to call this? Well, we'll rotate the rotor. And what's important here, we are rotating backwards. So other than with a regular rotation, we are now rotating in the opposite position. And then we adjust the turnover notch in position, in relationship to the wiring. Okay, yeah. So how do we rotate backwards? Right now we're only rotating forwards, and to distinguish between that, we'll now introduce a boolean up here, which we'll call forward, and we'll set that to true. So here, if forward, only then are we going to use this kind of rotation. Now if we are rotating backwards, well, what's the opposite of this really? So I'm going to copy this, put it down here. Well, here we took the first letter, position 0, and moved it to the end of the list. So now we're going to pick the last letter and put it at the front. And then we have everything up until that letter not included, and then we have done a backwards rotation. So forward is false. We rotate backwards. So here we'll now say self.rotate by, and this is important, n-1, because remember, ring setting, we are doing this historically accurate, so we are rotating by 1. This means we are not rotating at all, so we got to subtract -1 to go back to 0. So -1 is really because of the way that we do indexing with Python and computers nowadays, okay? And then we'll say forward is equal to false, because we are rotating backwards. And now we are adjusting the turnover notch. Okay, so the turnover notch, we first got to find out where it is. So we're going to call this n notch. And here we can just copy this alphabet string. And then we'll find our self.notch in that alphabet, okay? And that's then the position at which we are right now. And now we can adjust our notch. We can set this equal to the alphabet. And here we will now say, we'll index this to n notch minus n. There's just a slight problem with this. And this problem is, what happens if n is greater than n notch? Well, in that case, we got to jump back and come back at the end of the alphabet. And this is similar to, say you have a clock and it's 3 o'clock in the afternoon, and you want to subtract 4 hours from that. Now, you would never say it's -1 o'clock, even though you're subtracting 4 from 3. But what happens with your clock is, as you're stepping over 12, you're stepping backwards, you will then just start at 12 and count backwards from that. And in Python or in math, you do that with this particular operator, the modulo operator. So here, we don't have 12 letters, but 26 in the alphabet. So yeah, we'll use modulo 26, mod 26. And this is then essentially the same thing. So, and yeah, that's really it, I believe. Okay, I'm back in the main, and I'm just going to run this once more. We still get the same thing, but let's see what happens if we set this to 2. Let's run this, and there we go. We get a different result. So let's go back into the simulator. Now, Michael Koss implemented this with a letter string, but I think the historical machine, they had actual numbers there, but it doesn't really matter. Let's just go for B here and see if that checks out with what we have, YFLI at the end. And yeah, we get the same thing. And let's go for another ring setting. Let's go for 5, which is A, B, C, D, E. So we're going to make this an E. And then we're going to go for a Z, which is a 26 in our case. So let's run this. XELBN. XELBN. So yeah, there you have it. We have now implemented the ring setting. And with that, we have now a fully functioning Enigma machine. And yeah, I think this concludes this second part of the series. Now, of course, if you run this and you tell your friends, well, I have this cool Enigma machine, and here, see, this cool Enigma machine, and you run my, and if I run my code, then I get this cool output message which no one in the world can decipher, can decrypt, right? I don't think that your friends would be too impressed by this, because to them it's just like, well, you just randomly generated a bunch of letters. So our next thing, the next thing that we'll have to do, we have to come back up here to our animation. And well, right now this is not animated. This is just a picture. You can tell by these little arrows that I'm in my gallery here. But we'll make this an animation where you can then really see how everything fits together. And we want to be able to type out a message up here instead of just one character. And then we want to see how the rotors rotate and how we have a new encryption path for every single new letter. And that's really when your friends will say, oh, wow, you really, really did implement this. And yeah, I think this will be the next video. I hope to see you in the next one. And I think this is now where the fun really starts. See you.